Good day and welcome to the recorded version of the interactive webinar on diesel particulate matter, DPM, that was hosted on Thursday, the 3rd of June 2021. This event was sponsored by AMS Hayden, hosted by Fox in a Box, and fell under the banner of the Mine Ventilation Society of South Africa. All of the logos on the screen either were sponsors, people who participated, or anybody that had a hand in making this event possible. So thank you to all of these companies that we see up on the screen for pulling off a successful event on the day. The agenda for this presentation and for this recorded version: in the live version, we made use of an interactive tool called Poll EV so that we could get insights from the audience. So in this recorded version, you will see interaction from the audience on certain topics and certain questions. So just for some context for our viewers of the recorded version. And then we started off with some of the technical content, and we had Tanya van Dijk introduce us to DPM and the various health effects of it. Cecilia Pretorius was supposed to have a look at the occupational exposure limits for DEE and DPM, but due to some issues on the day, Tanya van Dijk covered that one as well. After that, we had diesel engine exhaust emission risk management and engineering controls, which was covered by Dr. Cas Badenhorst. Following that, we had Mr. Dion Swanepoel looking at DEE personal monitoring and tailpipe monitoring. After Dion, we had Marco Biffy speaking about working towards an integrated and feasible control strategy implementation. And finally, we had our friends from Australia, from PINSA, doing a presentation on fixed continuous real-time DEE monitoring solutions. With our first recording, the button was pressed late, so this had to be re-recorded. You'll see the interactive part of the session that we hosted also allowed the audience to give some encouragement to the speakers before they started out. So what Tanya is going to cover in this section is answering the question on what is DPM, what are the short-term health effects, and what are the chronic long-term health effects. Again, due to a slightly late recording, we missed Tanya's first slide. So on behalf of Tanya, I will just run through this slide for the recorded version purposes. So we start off this session answering the question, what is DPM? So diesel particulate matter is defined as ultrafine, for example, to have an aerodynamic fraction of less than 1 micron, allowing it to penetrate the lung alveoli. Although the classification of whole DEE exposure as carcinogenic by the International Agency for Research on Cancer only occurred in 2012, the concerns about the health impact that manifests from DEE exposure can be traced back to the 1950s. So it's been going on for a very long time already. The gases associated with DEE, primarily nitrous oxide or NOx, sulfur dioxide SO2, carbon monoxide CO, and carbon dioxide CO2 are not classified as carcinogens, however have various other health risks ranging from irritation, pulmonary pathology, and chemical asphyxiation.
DPM, therefore, is a complex and variable mixture of gases, vapors, and particles, as you can see on the figure there. Next slide. So we mentioned that diesel exhaust is classified as carcinogenic and not DPM itself. But since it is it's very complex to measure and analyze the full content of diesel exhaust for vehicles, DPM was selected to be measured as a surrogate for diesel exhaust. Currently, the magnitude of carcinogenity for diesel exhaust is not confirmed. So in other words, we know it is confirmed as a carcinogenic, but we are not sure to what extent. Next slide. So we mentioned that we use DPM as a surrogate to measure diesel exhaust. The reason being that it is a result of incomplete combustion of diesel fuel in diesel engines. In other words, it is a selective to incomplete combustion process specifically. So when we look at the components, we say it consists of an organic carbon and the elemental carbon portion, which adds up to total carbon. And when we look at total carbon, and we used to look at total carbon then as the marker because it represents about 80% of DPM. So it makes it a better, a good marker or a good surrogate to measure for. So I see most of you already looked at the question there. At this point, at the left-hand side of the screen, you can answer the question. The question is, do you know how to measure DPM in vehicle exhaust? So it looks like a lot of us do measure this and do know how to measure this.
Yes, thank you for those responses on the screen. So this was our first in-content question as we discussed earlier on. So you'll see this is how we have brought in the interactivity in the workshop. So as we go through content and you see a question on the slide, whilst the speakers are presenting, you can put your answer in. And if applicable, the speaker will just make a comment or two on this.
Okay, so if we look at the health effects for diesel exhaust, the short-term health effects associated with diesel exhaust may include headaches, nausea, coughing, difficulty breathing, tightness of the chest, and irritation of the nose, throat, and eyes. Next slide. We know the carcinogenity of diesel exhaust are the most prominent chronic or long-term health effect. And apart from lung cancer, it can also be associated with cancer of the bladder, the kidney, and the pancreas. Other chronic health effects include asthma, cardiovascular disease, and cardiopulmonary disease, which can include bronchitis and emphysema. So this actually concludes the health effects and the background that I have to say. And then the last question there, do you know how to measure employees' personal exposure to DPM? Okay, thank you from my side.
Thank you very much for that brief introduction, Tanya. And again, apologies from Kobus Dacker, who's fallen ill and couldn't present. So as we move to the next content, this was going to be presented by Mrs. Cecilia Pretorius, but Cecilia has also fallen ill. So the star of our show, the savior today, is Tanya van Dijk. So she'll also be chatting about occupational exposure limits. And if we can again give Tanya a nice hand of applause, like a heart, a clap. What she's going to be chatting about is just quickly exposure limits for diesel exhaust emission and diesel particulate matter, as well as occupational exposure limits for DPM. Before we go ahead, I do see that there are one or two hands that have been raised. So please, those that have raised their hands, go ahead and ask your question. All right, doesn't seem to be the case. Maybe the hand is trying to respond to Pole EV. If I can ask going forward, if you have a question, please drop it in the chat box and not just the raise of a hand. For us to facilitate the session, it's much easier to do it in this way. So without delaying any further, Tanya, you're welcome to take the floor again. And we're starting out with a question asking, are you monitoring against in-house OELs for DPM at your operation? If you are, what is the OEL that you're working with.
Yes, I forget that last one. Always you say that total what?
Right, so it looks like 50% at least are at 0.16 milligrams per cube, 26% saying no in-house, 20% saying 0.1 milligrams per cube. So thank you for these responses. We'll just allow a couple more minutes for them to come through. Not a couple more minutes, a couple more seconds, and then we'll get back to Tanya presenting the content on this specific subject matter. Tanya, when you're ready, we can jump to the next slide.
So in terms of exposure limits for diesel exhaust, unlike South Africa, internationally, the various countries do have exposure limits and leading practices regarding exposure limits for diesel exhaust. And since diesel exhaust is classified as carcinogenic, the approach in general internationally is to ensure that levels, when you measure levels, that it is as low as possible. The context of limits of the various countries is basically based on legislation as well as workplace and economic factors. If we look at a few of the countries' perspectives on OELs, we will see in the table below, for instance, the Canadians, they use a 1.5 milligrams per cubic meter limit that is measured as respirable combustible dust. The Mine Health and Safety Administration in the United States, they mainly use a 0.16 milligrams per cubic meter limit measured as total carbon, and they often also use to refer to the total carbon elemental carbon ratio. The Australians, they use a limit of 0.1 milligrams per cubic meter measured as elemental carbon, and then the Europeans, they have they basically use to refer to the directors in terms of carcinogens and mutagens. They don't really refer to a specific limit as such. So we can see internationally, although relatively diverse, they do have reference to OELs for diesel exhaust. So the next slide, Eugene. So we know now that where we stand with the rest of the world in terms of OELs for diesel exhaust, but where does South Africa stands in terms of exposure limits? Currently, you will know that you won't find any OELs for DPM in the Mine Health and Safety Act. The only reference to limits are the ones for the gaseous component, and that is in section 22.9. The Mine Health and Safety Council, however, issued an advisory note in 2013 where they proposed a phased-in approach to gradually decrease limits from 0.335 milligrams per cubic meter to a limit of 0.16 milligrams per cubic meter, measured as total carbon over a period of time. So it's like milestones that was set where they want us to reach a limit of 0.16 milligrams per cubic meter. So this is the approach from the mining perspective, and from the Department of Labor's perspective, they also propose to include DPM in a revised HASCEM regulation. That's still in process. So the next slide. The Mine Health and Safety Council launched a project whereby the current airborne pollutant exposure limits are reviewed, and although not finalized, a workshop was held in October 2020, and the following recommendations was made regarding exposure limits for diesel particulate matter. So they recommend, firstly, the inclusion of DPMs as a new pollutant in the Mine Health and Safety Act Schedule 22.9. They also recommend the limit to be 0.16 milligrams per cubic meter, measured as total carbon, and as well as a respirable fraction. And they propose to note it as a confirmed human carcinogen as well. So this is basically a summary for where we stand currently in South Africa in terms of OELs for diesel particulate matter. Thank you, Eugene.
Thank you very much, Tanya. Apologies that Cecilia's name is still on there. And again, thank you for saving us today and being willing to step in for both Kobus and Cecilia. I think you saw with the round of applause before you started your session that it is much appreciated. Before we move ahead, there's a comment from Tinus in the chat box just saying there's a significant difference between the EC OEL for metal mines and coal mines internationally. My question is whether we should consider adopting a EC OEL for coal mines and a separate EC/TC OEL for metal mines based on international practice and implementation. Above is related to personal exposure monitoring. So if I can invite any one of our speakers to respond to Tinus's question, you're welcome to unmute yourself. If there's anybody in the audience that would like to respond or add to Tinus's question, basically his question is whether we should consider adopting an OEL for coal mines and a separate OEL for metal mines based on international practice and implementation.
Gene, I'll just my comment. I'm definitely not opposed to that suggestion. I just think we need to be careful where one raises, or it raises to whom should that question be regarded to address to. Definitely correct. Coal mines focus more on the elemental carbon portion. Personally, I don't think there'd be a lot of value aside from confusion added if we do have two separate values in South Africa, and maybe just focus on the elemental carbon, which is, in my opinion, maybe a better indication because you've got less interference from the organic compounds, that organic carbon that could be present. So it's a fair statement, it's a fair question. I just think the question would be to whom would it be addressed and what would be the value added of doing that.
Dion, thank you very much for that. Is there anybody else that wants to add to this before I give Tinus a chance to respond to Dion's answer?
Sorry, Eugene, I've got my hand up. It seems to have lost promise. I won't do this again. But yes, I agree with Dion in terms of having perhaps one instead of two limits, if you want to call them at that. I know that some years ago, certainly in North America, there was a lot of debates because they used the EC/TC ratio of 3:1 at one stage, but it was soon discovered that that may not be the same for all types of fuels used and the type of mining. At one stage, the Americans, and I think they still do it now in the USA, there is no DPM limit in coal mines. From what I can recall, and I could be wrong, that may have changed over the years. So, and I know that Cecilia has also done a lot of work regarding EC/TC ratios, and she says there are variants in South African mines as well because of it. So I would tend to say if we can go for an EC limit and measure on EC, I think we may play it on the safe side.
Marco, thank you very much for that. Just to share with the audience, so when we did our preparation, I made a joke that this workshop will go faster because we have Marco as a speaker and not an audience member, where Marco he's a great audience member, always asks a lot of questions. So thanks for that, Marco. Tinus, please, you're welcome to respond to Marco and to Dion if you see a need for it.
Thank you, Eugene. I appreciate the response from both Mark and the previous speaker. I totally agree with what both of them are saying. The only concern that I have is looking at an Australian standard of 0.1 milligrams per cubic meter EC that is specifically focused for coal mines, if my memory serves me correct. I can be wrong there, but there's a significant difference between 0.1 and 0.16 for metal mines. And the 0.16 with the data that I have was previously referred to submicron metal mine standard. So that is where why I asked this question is whether we should actually, I agree, 1 OEL, it's better, but due to the significant difference between 0.1 and 0.16, that is where the question is, and why we are going for the 0.16 if international best practice is showing otherwise in different countries. Thank you.
Thank you very much for that, Tinus and Dion, Marco. Thank you for the rich discussion here. So if need be, we can discuss this a bit later during the Q&A. But for now, it's time for us to move on to diesel engine exhaust risk management and engineering controls. So while Dr. Cas Badenhorst is getting ready to take over and to talk us through this content, you can start giving him a thumbs up or a cheer or a bit of love with a heart, just to get the conference going. The content that he'll be discussing is exposure risk management, control framework for DEE and DPMs, some of the critical controls, innovation for cleaner, safer vehicles, the framework for DPM risk management maturity, and then the takeaways. So Cas, before you get going on the technical side, if I can just ask briefly that you introduce yourself, and then the floor is yours.
Thank you, Eugene. Good morning, everybody. As Eugene introduced myself, my name is Cas Badenhorst. I'm the Group Lead Digital and Occupational Health for Anglo American, and I'm also associated with the Northwest University on the Potchefstroom campus as an associate professor. Next slide, Eugene. So just a few bullets to get us starting, and the previous question and discussion around OELs is actually a very good starting point for me for this presentation. So traditional modes of managing DE or DPM have been on consequence management. So we focus on the disease rather than managing the cause, which is the control of DEs in the workplace and the prevention of exposure. I think the previous discussion actually highlights what I've got a problem with is we are so over-focused on the OEL and what the OEL should be and whether we use the right OEL, where I think we should have much more discussions around how do we actually control this in the workplace. You'll note I use the term DE, DPM sort of interchangeable. The difference was explained previously, so I'm not going to dwell on that. So whether I use DE or DPM, it's a reference to the risk we're dealing with. Where the use of DE, DPM controls have been identified, we continue to have failed or even absent controls resulting in exposure to DEs at levels over a given limit. We have historical over-reliance on regulated OELs versus up-to-date health science. OEL standards are also available across the world, and there is a lag that exists between advances in scientific understanding of risk and appropriate updates to OELs by regulators. To this end, it should be incumbent for us to reduce exposures to DPMs to levels as low as reasonable practical. If we've got science out there that tells us that we should really look at 0.1 elemental carbon as an OEL, then we should ask ourselves, why do we still consider 160 micrograms or anything higher if the latest science actually tells us differently? But as the latest or the last bullet there actually says that for carcinogen, there isn't actually something like a safe level. And we need to manage towards what is the low as reasonable practical. Next. So what's the problem here? And this is a very simplified sketch, but I do want to go through it to get us on the same page. We've got a source. Normally it's underground diesel piece of equipment. And the aim should be to actually prevent this source from emitting DPM. So ideally, at the source, we would like to use some controls. We might not be that good in those controls, or those controls might be absent. The pollutant then, DPM in this case, will find its way into the workplace. We're now dealing with a hazard. Our next option is then to put certain controls between the hazard and the employee. Again, where those controls are not that good or are absent, the health hazard, DPM in this case, actually get into contact with or in the vicinity of the employee, which now results in exposure. So we've got two ways in controlling DPM, either at the source or then along the path of the pollutant from the source to the employee. Next slide. Okay, so whilst you get going with the questions there, in terms of DPM exposure risk management, we follow exactly the same tool, we use exactly the same tools that we'll use for any other airborne pollutant or health hazard we deal with in the workplace. It will start with our baseline health risk assessment, from which we identify our unwanted event, in this case DPM emissions. We spend time to try and analyze and understand what are the causes and the consequences, what are the controls available to us, which of those controls available are critical, or the controls we want to chase in this regard. And then we work on understanding what are the specifications of those controls, how do we monitor those controls, what do we do when that control fails, and what corrective action do we need to take, and then also how do we actually maintain that control. You can find a lot more of this approach and the diagram in the ICMM document on critical control management. Next slide. So just to make it simplify that very complex flowchart there, we've got an unwanted event in the middle. The unwanted event in this case is actually DPMs being emitted from an engine. That result, as I indicated previously, in a hazard, being DPM presence in the workplace and employees getting into contact with that DPM. We can either put in some controls that will prevent diesels from being emitted or DPM being emitted from the engine. So that is sort of our preventative controls. Or we can also put controls on the right-hand side to actually eliminate or manage exposure if we can't prevent the emission. Those are called mitigation controls. Next slide. So if we then take that discussion slightly further and just a different view of those in the blue colors are the things we can do to prevent DPMs being emitted, and those in orange are the typical on the right-hand side. If we can't prevent the emission, how do we actually prevent the exposure? So our first point is our starting point at the top of our hierarchy of control is to actually look at, can we eliminate the production of DPMs at the engine level? If we can't prevent the generation of DPMs, can we actually then prevent the emission of DPMs from the tailpipe? If we can't prevent the emissions or can't fully control the emissions, then we can consider the design of our mine. That will include the design of our ventilation circuits and supportive infrastructure. If those controls are not good enough or are not sufficient to manage DPM, and we now got DPM in the workplace atmosphere, we can consider how do we actually prevent the exposure or how do we prevent the DPM particulates to actually reach the employee. We can do that through fleet management and DP fleet management plans, or as a last resort, the issuing of PPE, such as respirators or masks, and then on top of that, we can put in a program of exposure monitoring and surveillance, medical surveillance, to evaluate the impact or monitor the impact of DPMs on the health of our workforce. Next slide. So you can group those controls sort of in three pillars or buckets. The first bucket, look at our mine design, as indicated in our ventilation circuits, mine design for diesel vehicles, and in the later presentation, Mark will go through a lot of that detail. The second bucket of controls are sort of which I refer to as operational controls. That's where you get your typical emission-based maintenance program, fleet management, DPM, DE monitoring. And then the third bucket of controls are actually in the technology space. Now, how do we actually prevent DPM production or reduce production at the engine level? DPM emission reduced at the tailpipe, but then also DPM exposure reduced at the operator. Well, I see we are getting going on the answers. That's great. Next slide. So I'm going to step slightly to another track here and share with you some work that we've done at the ICMM, the International Council of Mining and Metals. In 2019, the International Council of Mining and Metals launched the innovation for cleaner, safer vehicles. And under this initiative, we actually brought together 27 of the world's mining leading companies. You can see depicted there, together with 19 original equipment manufacturers to collaborate in a non-competitive space to accelerate the development of new generation of mining vehicles. I think at the time, the industry realized that it is quite a challenge and we need to take hands and partner up with equipment manufacturers. Next slide. So 3 areas was identified by this initiative to focus on. Firstly, there was a safety initiative to consider the vehicle interaction and interaction between vehicles and people. Secondly, there was a ambition around the reduction of emissions of diesel particulate matter. This initiative specifically promote operational and technical innovation to minimize the impacts of underground mining operations from emissions of diesel particulate matters by 2025. So the industry has actually said through the ICMM, or let me actually rephrase that, the ICMM members, companies, have set themselves a target to eliminate diesel emissions underground by 2025. And then there's also a third ambition around greenhouse gases for more open cut operations, and again, to achieve greenhouse-free surface mining vehicles by 2040. Next slide. So this is quite a unique supply chain collaboration. And I haven't seen many similar collaborations across the world, where it's actually led by the CEO leadership from the participating mining companies, as well as the CEOs from the OEMs. So at the highest level of an organization, these initiatives are driven, and it just demonstrates the initiative importance and help to accelerate the pace of change. Secondly, it's a safe space for OEMs and mining companies to work openly, to help develop solutions and overcome silos within the industry and between companies, while still operating under anti-competition and antitrust rules. And thirdly, this collaboration represents a third of the mining and metals industry, giving some convening power of the ICMM in importance to achieving these ambitions, as it builds the widespread confidence needed to accelerate the level of innovation investments required to scale up commercial solutions. So very often in the past, what we've experienced is a single company talks to a single supplier to try and address the issues. And for these big equipment manufacturers, there's no commercial power in listening to one customer. But when you pull all the customers together and all the suppliers together, you're having a much different and a much more enriched discussion around getting to a solution. Next slide. So quite an innovative approach was followed. Quite a large group of these partners got together in London about 2 or 3 years ago, and that was representatives from the mining houses, representatives from the equipment manufacturers, both health and ventilation colleagues, but also engineering colleagues, maintenance colleagues. And the group spent about 3 days together to actually understand this problem and to really unpack DPM and DPM generation, not only from a mining operator perspective, but also from an equipment manufacturer's perspective. The team then, or the workshop then, spent time to understand what needs to be done, and how do we collaborate in getting it done by 2025. From that workshop and discussions, there was a number of controls identified which the industry, together with the equipment manufacturers, believed were those controls that would provide us the biggest impact in the shortest time span. Next slide. So all of that is actually available on the ICMM hub. ICMM referred to it as a knowledge hub. You can see the link there. You can follow that link, and that will bring you to a landing page, which is the copy here. You can then actually, and you don't need to be a ICMM member. This is in public space. And when you go into the diesel particulate page there, you'll find a number of case studies, which is extremely useful. So there's case studies from researchers. So for example, there's a case study on a case study from the University of Wollongong that talks to emission-based maintenance. So what it is, what's the value of having emission-based maintenance. There are case studies from other mining companies in terms of initiatives that they've, or controls that they've put in place. Quite a large body of knowledge sitting there. You're welcome to go there. There's also a page there that contains the various standards and regulations, and then also a database of technology and solutions that's out there. And this is still a work in progress, so we're building it. So if you ever feel that there's something you have done and want to contribute or share, you're welcome to actually submit it to the ICMM through your company or through the Minerals Council. He's also a member of the ICMM, and we can upload it there for you. But quite a useful reference to look at. One of the references you will find there is going to be covered in the next slide or two. So, please, Eugene. What we've developed is what is referred to as a DPM risk management maturity framework. So this initiative, so under this ICSV initiative, we developed maturity frameworks as change tools for mining companies to map current positions, motivate action, and measure progress. So typically you can use this tool to start building your business case or your business value case for your manager or for your site or for your company, how to change, how to mitigate your DPM in the long run. So what you'll see is on the, and I do have a next slide, but bear with me on this slide. You'll see we've got the three main buckets of controls there in terms of mine design, operations, and technology. And under them, we've got substreams, ventilation circuits, supportive infrastructure, fleet management, exposure monitoring, DPM production reduced at engine, DPM emission reduced at tailpipe, and DPM exposure reduced at operator. What we then got on the columns is what would each of those controls look like in its most immature, if I can use that term, level. So that's the level one. So that's basically how would that control look when you've got nothing in place. And then move on to a top level of maturement, level 5, where we've got zero emissions. So how would we expect ventilation circuits to look when we do have a level of zero emissions, or how would your fleet management look like when you've got zero emissions? So you'll see if you enter this page on the website, they are all interlinked. So if you click on any of those that are highlighted, it will actually take you into the underlying definitions and some explanatory notes of exactly what it means. Next slide. So as an example, I've taken the engineering control version, just blown up for you a bit. And if we look at, let's look at the DPM emissions reduction at tailpipe. So at a level 1 maturity, you would have no tailpipe emission controls. And then, as I said, as you go through level 2, there will be some more controls. Level 3, even some more. And where we get at a level 5 zero emissions, where you actually don't require, or where you actually don't require DPM tailpipes because you are on non-diesel powertrain arrangements. So what you then can do with this, next slide. You can benchmark your operations or your site against this self-assessment. So this is an example of one of our Anglo-American operations, where the red indicate our current status of that operation as in 2020. You'll see we've plotted it there in quite a simple view, and then where we want to be in the next few years. And what's useful is this, because this also gives you opportunity to decide which controls will you be pushing very hard. So in some of the arrangements, or some of your current operations restrict you to do some certain controls. So you'll note in this control, for example, DPM exposure reduced at the operator. So what that means is that refers to enclosed cabins on our diesel-driven equipment. Now, the current status is at that operation is that we do have open cabins. It's a low operation, so our cabins are open. But for us to change the equipment or the mine design to actually select that control or to make that control feasible is not a feasible option. So this operation has decided that for DPM reduction, operator will not be their key focus, and they won't push that to a level 4 or 5 type of maturity. Whilst you'll see something like fleet management or ventilation circuits, in their case, will be their key controls, and that's where they will focus their energy and their budget and strategy around. It's around getting the ventilation circuits optimal, manage the fleet optimal in terms of how many pieces of equipment at the end at a certain time, and then also getting the exposure monitoring, whether that's real time or personal exposure, get that to an optimal level. And that's their DPM strategy. And for them, it makes sense. They can now budget and plan according to this strategy. This might look very different for another mine, where you might decide that you got quite a bit of an old fleet, mainly a type, let's say tier 2 or 3 type of fleet. So DPM production reduced at the engine is not a feasible option for you. The mine doesn't have any plans to replace that fleet within the next 10 years. Then your key focus might fall onto tailpipe emissions, and your whole strategy might be designed around getting appropriate DPF filters on there and manage those effectively. So now where the expectation is to manage all of these controls up to a type of 5 ambition, but this gives you opportunity to actually inform a well-developed business plan or strategy that you actually can take to your management and say, we've looked at these options, this is what we can do, this is what we can't do, and now we can have an informed discussion around DPM controls. Next slide. So some of the takeaways from my side, I think we really need to understand the controls available to us. And not one is not better than the other one. And again, I think Marco will share a lot of information of us, with us around what controls are out there and how do we manage those controls. I think it's important for us to understand where you are as a company or site in terms of your maturity towards elimination of your exposure to diesels. And where do you want to be by when? I think it should be a discussion around the business value and the impact of the various controls as well. So it's not just around putting a control in place. The study I referred to earlier, and again, the case study is there, it's available on the ICM website, is a case study from the Wollongong University with a South 32 operation down in Australia. And the focus was around the value of emission-based maintenance as a control for diesels or DPM emissions. And the study has clearly shown that by having a detailed emission-based maintenance program, firstly, you actually reduce the number of breakdowns that you've got in the phase, therefore just actually increasing operational efficiency and operational time. But what was quite interesting about that study, it proved by managing diesels by a detailed or a comprehensive emission-based maintenance program, the site has actually proved significant diesel consumption reductions. And at the end of the day, when we went through the analysis of that study, it was actually a no-brainer to do it simply because of the diesel savings that the mine were able to achieve through that. So I think it's important that when you look at these controls, when you do your propositions, look at the total picture. You know, look at what are the other business benefits, just besides playing the health card. You know, we need to do this to reduce exposures. That's an important card, but that shouldn't be your only card that you play at the time when you need to promote or when you need to ask for resources to manage diesels more effectively. Cross-discipline collaboration is critical. You know, as occupational hygiene and ventilation specialists or practitioners, we can tell the mine what their problems are, you know, and we can tell them what to do. But when it get to the actual doing of the stuff, you know, when we get to maintaining diesels, when we get to putting in filters, maintaining filters, that needs real cross-discipline collaboration with our supply chain colleagues, external collaboration with suppliers, etc. This is not a one-man show. And if you think it's going to be a one-man show, you are setting yourself up for failure. Going through this motion, I think it's also important that you start building readiness to adopt technologies. You know, whether it's the adoption of DPM filters, whether it's the adoption of plant maintenance. This involves quite a bit of change management from the engineers, from our maintenance people. So it's not as simple as slapping on DPM filters and there you go. There's a process. We need to start building that readiness. We need to start engaging with our maintenance crews for them to understand why this is important. What, for example, a filter should be doing, and actually work with them to take ownership of that control and not trying to manage that control out of our ventilation occupational hygiene offices. Jean, I think that was my last slide. Thank you very much.
Gus, thank you very much for that insightful presentation and for sharing your knowledge on it. Our next session is going to be done by Dion Swanepoel from the Sayenzi Occupational Hygiene. We have a break scheduled at 11:15, so we'll just see how long it takes Dion to run through. Dion, I might stop you in the middle. Let's see whether we can finish it up before 11:15. If not, we'll take the break and just head back and finish up your section. So before Dion gets going, again, we can give him a bit of support before he takes the floor. So what Dion's going to be speaking about is DEE personal monitoring and tailpipe monitoring. And he's going to cover inorganic gases, organic vapor, and DPM under personal monitoring, and then also chat about tailpipe monitoring. Dion, before I give you the opportunity to just introduce yourself, a statement from Tinus, just saying totally agree with Cas. Primarily prevention and elimination is much better than cure. At the end, we have to measure the effectiveness of measures taken against an appropriate standard on the emission side and personal. Totally agree with your approach, Cas. Great presentation. Tinus, thank you very much for that and for the kind words to Cas. We fully agree on our side. Dion, the floor is yours for a quick introduction, and then we can get going with your presentation.
Fantastic. Thanks, Eugene. I just gave myself a heart, so I thought I just have to maybe communicate. I'm Dion Swanepoel from the Sayenzi. I'm currently enrolled for a doctorate at the University of Wollongong in Australia on emissions-based maintenance. And today I'm going to take us through personal monitoring and then source monitoring, just an overview on that. So Eugene, if you can take me to my first slide. So by the end of this session, hopefully we'll have more clarity regarding during DPM sampling, when should we use an impactor? How can we use a static sample to evaluate our diesel engine exhaust health risk? And some general pointers on how to accurately collect engine exhaust data, diesel engine exhaust data. Cool, next slide, please, sir. So this session, I'll be looking at personal monitoring. So I will include the inorganic gases, organic vapor, and the DPM portion. And then also the fundamentals of source monitoring. Maybe as a bit of a disclaimer, today's session is geared more towards transferring knowledge to our young professionals. So the guys the 50% of people that say they are not 100% comfortable with DPM sampling on their own. But I do hope there'll be some knowledge for everyone. A key takeaway. Our next slide, please, sir. So the very fundamentals of exposure monitoring, we take our samples within the breathing zone. So we have a 30 centimeter semi-hemisphere from the nose. And then hand in hand with that, we do our sampling duration must be sufficient to represent our exposure duration and to collect enough of the pollutant that we're investigating. So this principle will apply for all the hazards that pertains to diesel engine. Next slide, please. When we look at our inorganic gases, our carbon monoxide and dioxide, we most commonly use direct reading instruments for our monitoring. So out of curiosity, I'm not sure if you ever wondered why we would use direct reading instruments. My takeaway is because a high dose will induce an immediate effect that could be fatal. So we want immediate results. Actually, we don't want immediate results. We want early warning. We want to have a warning before a person is actually exposed to a high dose that could be fatal, could have an acute health effect. And we don't want that information 2 weeks after the exposure occurred. So where we anticipate high nitrous oxide or dioxide exposure concentrations, it's also recommended to use a direct reading instrument. Alternatively, there is passive and active sampling options for NOx sampling. Next, please. When we look at organic vapor, so for volatile organic compounds, we have an option of either using an active or a passive sampling method. For example, NIOSH 2549 is an active sampling method. And what's cool about this method is it's a screening method that quantifies a large range of compounds, which includes benzenes and aldehydes, both that is associated with diesel engine exhaust. For polyaromatic hydrocarbons, the method I'm most comfortable with is the NIOSH 5515. It uses a filter and a sorbent tube in series. The filter collects the particulate PAH portion and the sorbent tube collects the more volatile portion. And I'm not aware of any passive sampling options for PAHs. Next slide, please. So to assist with your mental imaging, at the top, we've got a PAH sampling train. So we've got the filter portion that's with the green tape, and behind that is a sorbent tube that's connected, and it's covered with foil. Below that image, we've got an example of a charcoal tube that is used for active VOC sampling. And to the right, a radialo diffuser or passive sampler for VOC sampling. Next, please. Some of the common mistakes that I've encountered concerning the organic sampling. The biggest one is probably incorrect sampling storage and transport. Because we are dealing with volatiles, it needs to be stored and transported at low temperatures to preserve the sample integrity. Another one is incorrect sampling duration and flow. So typically what happens is the sampling duration is not sufficient to collect a large enough quantity of air to actually quantify the compounds that we are interested in. And then the biggest problem that I typically encounter is sampling methodologies that are incompatible with the analysis. So as a rule, always check with the lab that you're using. What analysis methods are they using? They would give you advice regarding the sorbent tube material. For argument's sake, should you be using charcoal or silica gel to collect your pollutants? Next slide, please. So in terms of the particulate phase, the very basic principle of DPM sampling, the method probably used most throughout the world, definitely the one I'm most familiar with, is NIOSH 5040. It requires a 37mm quartz fiber filter, and you have an option of a flow rate between 2 to 4 liters per minute, depending on what the anticipated exposure is. Cool thing about this method is there's no special storage or transport requirements. Next, please. A bit more on the technical side, one of the questions, or some of the questions rather, that people often ask is, how should the actual sampling train look? Should it be open phase sampling, closed phase sampling, or should we use a size selective like a cyclone? And here you can see the difference between the different sampling trains. On the left, we have a cyclone. The top, we've got an open phase sample, and at the bottom, a closed phase sample. So the good news is it doesn't really make a difference to the results which approach you use. So a study done by Pretorius and Grevie indicated that all three methods would give you similar results. So it becomes a question of dealer's choice. Something to take note of, open phase sampling is prone to tampering either by adding foreign particles or operators with curious fingers that start poking at your filter. Personally, I'm a fan of using a cyclone, and the reason is you get a more even deposition of the pollutant across the filter. And also it prevents them wandering fingers to start fiddling with your filters. Next slide, please. Another important question is, when should we use an impactor? So there's a PolyV question for that. I'm maybe going to give some just short amount of time for you guys just to get your own ideas. You can see an illustration of an impactor. So you've got the filter at the back, the impactor at the middle part, and then it's also attached to a cyclone. I'm going to give about 3 seconds more. Fair enough. What is an impactor? Fair question. So impactor is it's also a size selector device, and it's designed specifically for the sub-micron part. So to answer the question, when should you use one? It really depends on the background exposure. Any carbon-containing particles will contribute to the elemental carbon of your analysis. So if carbon-containing particles reaches your filter, it will be analyzed as elemental carbon. So coal dust is a prime example of this. I'll definitely use an impactor in the coal industry. Or if there's any other carbon-containing particles, for example, coke or calcium carbonate. If you're not in the coal industries and you're confident that there's no carbon contamination, you generally do not need an impactor. So it's not a default that you must use it. It's really in case specific if you do have a carbon background that could interfere with your elemental carbon. Next slide, please. Some of the biggest shortfalls that are observed from DPM sampling. The first one is not having a field blank as quality control. The reason it's important is the quartz fiber filters tend to have an organic carbon residual. So earlier we spoke about the total carbon with the organic component in it. So if without a control filter, you don't know if you should adjust your results accordingly based on that background organic carbon component. So you might very well be overestimating your exposure if you're looking at total carbon. The other mistake is using the wrong sampling media. People often send PVC or MCE filters that they use for their particulate exposure, and then they want to sample that for DPM, which is something you can't do. DPM analysis is very specific, and the technique requires a specific sampling media. Next one, please. again, just to gauge your own approach, do you guys use static samples? Do you see value in static samples? Fantastic. So this diagram I've conjured with the idea to illustrate how I would go about to use a static sample or area sample to assist with health risk assessments. From my experience, static sample exposure tend to be higher than your personal sample. So obviously, this is a very nuanced statement, and you actually need to know the workplace and where the areas are of concern and the areas with the high exposure. So for underground, this would typically be in a return airway of the area with the most vehicles. So I'd start by sampling there, for static sampling there, and especially for the PAH and VOC screening, with the idea that you're almost concentrating your pollutants in one area. So if my static sample comes back above a specific criterion level, argument's sake, 10% of an OEL, I'd verify that exposure with personal sampling of the highest exposed individuals. If it's below 10%, and I'm confident and comfortable that I've identified the highest exposed area, I think it's reasonable to suspect that the personal exposures will be lower. So again, provided that you do not anticipate any other high-risk employees. So you need to have some knowledge of the process. If the risk is unacceptable, we need to go and have a look at what controls are in place and the effectiveness of those controls. If the risk is acceptable, we can continue with our hazard documentation and compliance sampling. Cool. Next slide, please. We're going to move over to the source monitoring. The basic constituents of a tailpipe monitoring is a water trap. The name is fairly self-explanatory. It reduces the moisture in the exhaust. An exhaust mixing unit. So the purpose is to get our exhaust gas mixed homogeneous and also to cool the exhaust gas temperature. And the final component is our monitoring equipment for either the gases or particulates that we want to investigate. Fantastic. Cool stuff. Thanks. So here you can see a probe that is going into the tailpipe, and then from there, which off screen that you can't really see, from there it will go into a water trap and then into the mixing unit in white there at the back with the copper heatsink. So this is almost the ideal ideal approach. And what you'll find quite often is that probe is directly connected to gas or any form of instrument, which I'll elaborate on a bit later, but it's not good practice. The next slide, please. So here you can see all the different components of a tailpipe monitoring system. So at the right, the silver is the water trap that reduces our water vapor. From there, it goes into the mixing unit that also cools the exhaust temperature, and the emissions or the hazards that we're looking for, the components of the diesel engine exhaust, are measured from the mixing unit. So it's not directly measured from the tailpipe. So some of the biggest pitfalls that I've counted so far is measuring directly probe connected to sensors from the exhaust. And the reason why it's a problem is there's a good chance that you're going to burn your filter, your sensors, which is the first one. Then there's also virtually no repeatability or intra-vehicle comparison. And the reason is your velocity within your exhaust changes if there's any bends in the system. So if you're taking a direct measurement directly from a tailpipe, there's a good chance that the placement of your probe will influence your results, which is not scientific at all. So the reading can't be dependent on the placement of the probe. And if you're going around a bend, you'll have different velocities, you'll have different mass flows, which will in the end influence your results. Eugene, you just go to the next slide for me, please. Okay. So the biggest pitfalls when it comes to tailpipe monitoring, the first one, as I've mentioned, is pushing the probe directly into the exhaust. The other one is not having a water trap. So especially if you're using light scattering techniques to determine your particulate phase, your DPM portion, any water vapor in your exhaust will be contributing towards your particulate phase if you're using light scattering. So you're going to overestimate your DPM component if you don't account for that water. So that's one of the big problems that occurs. The other one is not reducing your gas temperature. If you look at the EPA method, you should actually bring down your exhaust temperature to at least 50 degrees Celsius or lower. As soon as you've got a higher temperature, we've got changes in air density, which will also again influence your concentration. And probably the biggest mistake that I encounter is only taking one measurement. So typically at the very end, we'll take a measurement after the after treatment. The issue of this is you can't determine the efficiency of your after treatment because you only have one value to compare to. So we tend to use tailpipe monitoring and emissions-based maintenance as interchangeably, but it really isn't. It's two different concepts. Tailpipe monitoring typically is a single measurement and you evaluate your results against a specific criterion. It does give you usable information, but you need to compare it to something, either internal or limits-based maintenance, on the other hand, it's a program that gathers information from the engine as well as from the diesel engine exhaust profile. So it's not just a single measurement. It actually gathers information from 6 different systems that relates to the engine and investigates and to glean information to make a diagnostic about what maintenance is needed to change the emission profile. If you can just go to the last one for me, please.
Dion, before we move on, just a comment from Cas in the chat box. So Cas just says the technical complexity of tailpipe monitoring should not be underestimated. Be careful of those plug-and-play instruments. Would you agree with this statement, Dion?
I full-heartedly agree with that statement. It's definitely not as simple as just pushing your probe and a sensor into your exhaust. Again, there's value to be gathered from that. Aside from burning your equipment, aside from that, you've got no repeatability, which burdens any value that you could derive. So now I completely share the sentiments. There's a specific tailpipe monitoring is not as simple as just rocking up with equipment and starting to get measurements. There's specific protocols that should be in place. You should be decreasing your exhaust temperature. You should be accounting for the water vapor in a water trap, and you should be getting that gas mixed. So completely agree. And also what information that you're gathering. So if you go to my next slide, I'm going to elaborate a bit further on that. So if you look at the point mark 6, so what I'm trying to illustrate here, this is all the systems that emissions-based maintenance is gathering information from. So it takes information from your air intake, it considers oil quality, diesel quality, your cooling system of the engine, and then the exhaust system. So when it comes to the exhaust system, emissions-based maintenance is actually taking at least 2 measurements, one from the manifold coming from the engine, and then one after the after treatment. So that's what I tried to indicate there by the number 6. So you get a diesel engine exhaust profile. So you get an idea of what is coming directly from your engine, be it your particulates, carbon monoxides, and then one after the after treatment. So if you don't see a reduction before and after your after treatment, you know that either you've got a blown out filter or after treatment, or there could be various other mistakes. But the point is, it gives you something to compare to opposed to only take one measurement and you make a call whether you're comfortable or happy with the result at the end. So definitely even though we use it interchangeably, emissions-based maintenance is definitely a broader program. The whole purpose is to make a decision regarding maintenance in how to change that profile. So it's not a once-off measurement that you've evaluated against a specific criterion. You could have internal standards to evaluate it against. That's not the problem. The point is you want to, especially if you're using technology, you want to have an idea of how well is my engine performing, how well is my after treatment performing. I think that this should be my last slide. If you can just...
Dion, before we check, just a comment from Marco in the chat box, just saying he also agrees engine duty cycling also plays a part. And that was your last slide, but you're welcome to add to what Marco said in the chat box if you see it to be fitting.
I don't think I can really add anything. I mean, he's absolutely correct. Thinking about emissions-based maintenance in the broader scheme of things, it also contributes to what Prof. Kas was saying a bit earlier. The first form of control, for one of the stops of control, is to get your engine to emit as little as possible. So directly from your engine, you want to have either as little as possible carbon monoxide, because that means you actually have proper combustion. So that's where your fuel consumption saving will come from. You want to have your particulates to low as possible from the engine. And then only after that, your after treatment comes into play to further alter or manipulate the constituent that you are having control over. So no, completely agree with what he's saying. It's a fascinating topic, but it's definitely not just a quick jam a probe with a sensor into an exhaust tailpipe, get a result, and then move from site. So, but cool, that's my story. You're welcome to elaborate. Thanks for listening to me. I'm Dion Swanepoel.
Dion, thank you very much. And before we move on to the second to last section with Marco, just in the chat box, Francois saying agree with you, Dion. The problem is free acceleration monitoring versus underload and underground versus above ground measurements. So Dion, thank you very much for your time for putting this together. And to the audience, right at the end, we'll share contact details of all the speakers if you want to get in touch with them to discuss some of this in further detail. But without further ado, we'll head to our second to last presentation of the day. It'll be done by Marco Biffy, titled Towards an Integrated and Feasible Control Strategy Implementation. So let's give Marco a hand and a heart and a thumbs up. He'll just give a quick introduction, discuss the hierarchy of controls, look at the control measures, the integrated approach, and the future scenarios. So Marco, before you get going, if you could just do a brief introduction to yourself, and then we can hit the road.
Thank you, Eugene. Good morning, everyone. I'm Marco Biffy. I'm a mechanical engineer by training, but I spent over 35 years in mine ventilation and a couple in industrial ventilation and air conditioning systems. So what it means is that I am a jack of all trades and definitely a master of none. And I hope that going through this presentation, it's going to help putting together some of the thoughts that I've had over the years and shared with the likes of Prof. Badenhorst. We started looking at this, I think, in about 2009. And we finished doing this together in 2019 when we started with the ICMM subcommittee. And then I retired after that. So we'll go through a brief introduction. We'll look at the hierarchy of controls, and I want to take this from a different angle, perhaps than what Kas perhaps has covered. And then line up with an integrated approach. In doing the hierarchy of controls, Can you go to the next slide, please, Eugene? I want to look at things also from a perspective of elimination very briefly. So why are we here? It's because there are levels of increasing mechanization, particularly in the South African mining industry, because it is believed that mechanization is the answer to industry demands, and also because we are in a competitive global market, and what the Americans, the Australians, the Russians are doing, we need to do better to make a profit. Also, there is a belief, which is correct, that worker exposure to risks or hazards is reduced to mechanization. And I'm not necessarily talking about diesel emissions here. I'm talking about workers not being exposed to rock falls and similar type of incidents, and also working towards a continuous mining process for hard rock mining in particular. In terms of South African mining in particular, the narrow reef operation, okay, let's start with coal mining and base metal mining. Massive ore bodies are very comparable to what we have in Europe and overseas. So the issues and the problems are very common. However, in terms of a narrow reef operations, mechanization becomes an issue. We've got our traditional layouts and mining methods. The hard rock bodies on the reefs, so they're quite unique. And what we typically do from our side is we use a sequential ventilation strategy, which means moving air from one panel to the next. And this becomes a serial pollution problem. And at the end of the day, it is the use of diesel power vehicles is deemed advantageous because they are quite rough and rugged, and they can get just about anywhere in a mine. So that is those are the issues that we have to face. Next slide, please. So in terms of the hierarchy of control, in terms of elimination, we will look at diesel-free equipment, and that's something that we need to perhaps consider for new projects. And there may be some answers there that don't necessarily mean batteries. Anyway, we would like to then, in terms of substitution, looking at diesel engine technology options, which you'll see package everything in one. In terms of engineering the existing equipment, we should be looking at low-emission diesel fuels, lubricants, and additives. Anything that gets burned in that engine could become a nucleus for the attachment of carbon and other metals. Sorry, not that carbon is a metal, just carbon, metals, and other substances that can then enter the lungs. Exhaust after treatment is a very good way of handling that. Equipment maintenance, in terms of exhaust maintenance systems, as was discussed earlier, and of course that needs new competencies and equipment, and ventilation system design. Again, if we could use ventilation on demand and bring in fresh air for every panel in a board and pillar platinum operation, we would have a lot less in terms of problems than we're having at the moment. In terms of administrative controls, one would have to look at diesel exhaust levels in working environments, which is a little bit too late, working or measuring worker exposure, and then the use of PPE. Again, I think the secret here is to say, try not to release the emission into the atmosphere. That should be a good strategy to start off with. Next slide, please. So where we are at the moment is that we have mobile equipment and we use tier 1, tier 2 diesel engines. We can talk about tier 3s in a second. And we go to 50 or 10 ppm even diesels in the hope that will improve things. Exhaust filtration is added in most cases, especially the older equipment. And if you're using or if you're in a narrow reef operation using ultra low profile equipment, you will find there is usually a problem to fit exhaust filtration systems after the machine has been manufactured. And failing which, we try and dilute as much as possible using ventilation, and hopefully we're using air that's not being used somewhere else where a diesel engine was operating, and then we go for respiratory protection if that is necessary. And you'll see that we can use enclosed cabins, if necessary as well with filtration. Next. Now, going a new route is very similar, but we are going to be using, or we can use, higher specification engines, which are kind of pre-packaged, if you will. And as I said, we'll chat about it in a second, with ultra low particulate diesel. Next, please. Alternatively, you can look at electric, which means battery or fuel cell driven. Next, at the moment, we are stuck in what I call the diesel paradigm, certainly for the short to medium term. Next, please. So let's start from the bottom. What can we do right away? In my opinion, electrical hybrid units are probably the best. Okay, if you think of this LHD as good tram, even in our narrow reef operations, they've come to substitute scrapers, if you think of it. So it just moves up and down in a straight line from the bottom of the gully and tip into the ore boss. There's no reason why we could not tether the unit by means of an electric cable. And what I mean by it is small engine, diesel, which will allow the unit to move from one gully to the next. But when it does mucking and loading, that's when the most diesel emissions are generated. That's when the most heat is generated. So if we can do that by means of an electric motor, which is plugged into the wall, why not? Next slide, please. Okay, let's very briefly talk about lithium-ion batteries. Lithium-ion batteries are basically rechargeable units. We use them in our cell phones. We use them just about anywhere. And it's just a question of running a current through to charge it, and then when it discharges, it will do the work that is necessary. Next slide, please. Okay, let's concentrate to the picture on the left, which is less busy than on the right. Fuel cells. What fuel cells are electric absorption system. The fuel that comes in on the left at the top is a metal hydride, which releases hydrogen as it goes past the anode. And that is due to the presence of a catalyst, a platinum catalyst. Now the hydrogen is then split into electrons and positive hydrogen ions, as you can see there. The electrons basically go away and do what electrons do in a current, which is move the motor and return to the cathode. The hydrogen ion then migrate to the cathode inside the cell, and we then supply air, as you can see on the right-hand side, which is rich in oxygen. And again, through the action of another catalytic membrane, the oxygen reacts with the hydrogen ion to produce water vapor, which gets out of the exhaust. Now, the only other thing that needs to happen is that the fuel that you see leaving on the left-hand side at the bottom has to be recharged with hydrogen, which is this metal hydride fuel. It's almost like you have in refrigeration absorption plants where you have ammonia being desorbed at different temperatures. The point that I'm making here is that somewhere along the line, in the mine or on the mine, there has to be a metal hydride tank to be able to replenish the hydrogen. Next slide, please. Okay, this is just putting things in perspective. You'll see at the bottom is the mileage per day trip and the weight of the vehicle on the vertical axis. What you see is that for different vehicles, depending on the average mileage of travel and their weight, there are different preferential systems. The first being the battery electric, which is a lithium ion. Moving on to the fuel cell electric, which is quite a big chunk, and you can see the trucks are in there somewhere. And then the last one at the top is for airplanes and ships. But if you can press again, please, Eugene, what it should show is that the mining equipment that we certainly use underground falls in that area, which makes it, suitable for both battery and for fuel cells. Next slide, please. So far, if we're talking about elimination, it requires quite an intensive and effective change management effort. Will take time, resources, and planning. And that's a misspelling for me. It's starting now, especially if you're working on an operation which has 20 years ahead of itself. It's mechanized with diesel. You can maybe schedule the entry of electric equipment into your mine. With an exchange when the diesel equipment is due for change. School fees are not fully paid up. Expect to climb a very steep learning curve, and it requires very much upskilling of your workforce. However, the technology is cleaner, more efficient, and healthier, and of course it's green. But last point is we don't know what we don't know. Next slide, please. I think it's a question. So the question is, sorry, Eugene, you take over at this point.
Thanks, Marco. You're welcome to proceed, but I'll take this one. So the question is just saying, or asking, do you know how a hydrogen fuel cell operates? For those who might have forgotten, in the chat, I've just put the link to PolEV again so that you can respond to Marco's question here. So you can just click on that link, enter a username and start responding, either on your mobile device or on your laptop or desktop. And we can see the results coming through, and they are almost a three-way tie. Marco, you're welcome to jump in with any comments on this from your side.
And yeah, look, as I said, this is basically the ideal solution because we're taking the diesel away, and it's something that because the majority says no, not certain, it's something that is going to play a big part in the future, in my opinion, or that it should at least, but it's some way away. I'm ready to go on to the next slide, which was supposed to be before this question, but not a problem.
Great, thanks for that, Marco. We'll head on to our next slide.
And what I wanted to say with the next slide is that we don't know what we don't know. That was the last bit. And this is what happens. This is probably the first battery electric vehicle fire on record, or at least it has been investigated. And what it is, it's a cassette unit. The engine is up in the front. So the battery is sitting in the front. There are 3 batteries, and on the right, it's a picture that was taken by the 2 technicians that were there when the fire started, and they were fortunate enough. This is in North America, by the way. Fortunate enough to take this picture and come out of it alive. But what happened here is that this is being a battery. it released it released all the energy stored in that battery, in those 3 batteries, in a very short period of time. And what you can see is that, of course, the rubber and everything else burned on the left-hand side, but the back of the unit is kind of pretty unscathed. And the fact that these guys were sitting at the back, and that's why the airflow was from their back towards the fire, and that's why they made it out alive. But again, it's things that we need to learn about how to manage these very, very powerful batteries. And may I suggest again on the side that even batteries that are used in normal diesel units should have some kind of a, call it a fuse. If they start running away, they release quite a lot of energy. Next slide, please.
Thank you, Marco. Our next slide is another question, so I'll run with this one. So the question up on the screen is just asking, do you understand diesel engine classification, the tier or the euro? Let me just change the settings here so we can see how many responses we're getting. So we've got 33 responses, 40 jumping up quickly, and about half saying yes, we do understand. Marco, from here, you're welcome to take over.
Okay, can we perhaps go to the next slide if you're ready? And this is what I want to talk about now, is diesel engine certification. Having accepted that we're going to have to live with diesel engines for a while yet, we are going to do something about it. So we're going to have to live with it, but also we need to understand what can be done to minimize the risks to acceptable or reasonable levels. And I'm using the ICMM wording, which links into the definition of carcinogenic substances. Next slide, please. Now, this is a pretty picture that shows what engine certification is all about. On the left-hand side, we start with a tier 1. And in terms of certification, one looks at the production of particulate matter, which is the vertical axis, against the nitrous oxides produced by the engine that's being certified as it undergoes a bench test. As you can see, the green block is represents non-road vehicles in the range that we use in our underground mines in particular. So when it went from tier 1 to tier 2, there was a 20% reduction in hydrocarbons and NOx, and a 50% in particular matter. So what it means is that for a tier 2 engine, the emissions in terms of particulate matter in grams per kilowatt hour of engine energy emitted is around the order of about 0.4 grams, whereas at the same time, the NOx and hydrocarbon is going to be less than 6 grams per kilowatt hour. And the others you can see, sorry, can we go back up? The others you can see how they reduce, and the kind of comparison can be made between a tier 1 engine and a tier 4 engine in terms of those emissions. One thing I want to point out is that Africa, where we are at the moment, lots of tier 2s, and a lot of people are clamoring for tier 3. And I know that some mines have purchased tier 3. Please note, tier 3 in terms of DPM is the same as tier 2. Tier 3 is just a considerable reduction in NOxes being emitted. Next slide, please.
Marco, just before you move on to the next slide, there's just a question from Andre saying, do you think for planning purposes we can still use 0.065 to 0.08 cubes per second per rated kilowatt?
Andre, my answer to that is no, and I will cover it in the next couple of slides. Can we have the next slide, please? Okay, this is a final tier 4 engine. What is important here is to look at the complexity of this. You've got the block, You got air coming in, goes through a turbine, and then it goes through an aftercooler. It mixes with some of the, that's what the EGR cooler is, mixes with some of the exhaust coming out of the engine in order to make sure that what's particularly haven't been burned some more, gets introduced, comes out of the exhaust through the turbine, and then it enters that little cylindrical, which is a filter, which is the first cylinder, which is a DOC DPF. So the first one is a diesel oxidation catalyst, which attempts to get rid of the carbon monoxide through oxidation. And then the DPF is a diesel particulate filter, and then it goes through yet another set of filtration, which is the selective catalytic reducer, and it uses an ammonia oxidation catalyst to convert mainly NO2 to NO. Now you can see there that it's quite a complex system. The DEF tank is the diesel exhaust fluid tank, which those of you that are riding Euro 6 diesels, motor vehicles may be familiar with. That contains ammonia, and that is essential. So you can see there is a lot of controls going on to try to get rid of the carbon monoxide in the first stage with the diesel particulate matter, and then going through the next stage to oxidize the NOx into NO, and into reduce, not oxidize. Next slide, please. Okay, here we come to the question that Andre, you were looking at. This is work that we did at Anglo American with Sasol and Diesel and Deutz Diesel, and with the CSIR. And what it was a set of tests that were done in 2016, where we looked at the performance of a number of things, different types of fuels, with the same engine, which was a Tier 1 engine, and different types of diesel particulate filters. This is in its simplest form, is that the basic one, which is a diesel oxidation catalyst with a sintered metal filter. That's what SMF stands for. And what we could achieve here, next slide, please, or next button, is a 30 to 60% reduction of particulate. And here we were focusing on particulate matter, but the paper that was presented at the MBS conference in 2016 provides all the results for the gases as well. But we had a 30 to 60% efficiency based on the type of fuel that we used. And here what I want to say about fuels is diesel engines are a typical example of garbage in, garbage out. And the garbage out is DPMs. So the important thing is that the quality of the fuel is very important. We looked at biodiesels as well. I wouldn't scream too much about them. I think that 10 ppm or less, if you can get it, sulfur are good for your engines, whichever ones that you use. The DOCN filter is a full flow stream. If you answer the question that's just popped up from my namesake. It's full stream, it's a sintered labyrinth type module. And the next one that you see below is the active. So what you would do with that, once it becomes, you're measuring the pressure drop across the filter. Once it becomes too high, you know it's clogged, so you take it out, put in a new cartridge, you take your cartridge and you go and wash it out. And then wait for the next change. The picture that's just come up below there is for an activated type unit that has regeneration. So that little bit of orangey stuff between 4 and 5, that's actually a heater which burns whatever DPM is left after the filter. So if you can press the next button, please. it should come up saying that the efficiency we found to be 99%. Again, the point is that the geometry of these units to fit in narrow equipment is an issue, it's a challenge. So unless the OEMs come on board, it will be difficult to achieve this. Next slide, please.
Marco, before you head to the next slide, just a
Yes.
question from Dion. What percentage of after treatment is considered to be good?
I would say, again, depending on we were taking measurements based on, on the fuels, but, again, I'm sorry I don't have the graphs in front of me, but 99% means it got rid of 99%. There was only 1% DPM left of the, I'm just trying to remember, but basically it's 100% would be perfect. So it gets rid of all the diesel particulate matter. And this was done at the Sasol laboratories, which have got the equipment, and Dion, I think you know them well as well, to do this kind of stuff. No, they were not. The other question was, this conducted with a natural work environment? No, they were not. They were done on a bench, but what we did do, we went to one of our mechanized mine, Angler, and what we did, we monitored the engine cycle for a typical LHD. And then we replicated that cycle with the use of the computer at the Sasol lab. These are the labs that used to test the Wolf Formula One engine, by the way, many years ago. So that was, they were used in that cycle. And that's why I mentioned cycling earlier when Dion was speaking. So it wasn't taken just haphazardly. It was taken over the same cycle using different fuels, different filters. We did about 20, 30 experiments. And this is what we came up with. So these regenerative type of filters can be quite effective if you can fit them to the engines in use now. And importantly, guys, I repeat, low sulfur, because the high sulfur will poison your catalysts in that filter unit.
Great, Marco, thank you for that response. I'll get to the next slide for us.
Okay, so how are we going to be talking about instruments? How are we going to integrate this? We got measurements, sorry, instruments that measure worker exposure. There are instruments that do real-time environmental concentrations, and there is vehicle monitoring instruments, the tailpipe ones, the emission-based management ones. So next slide, please. So what's important here is that we got 3 sets of instruments that measure 3 different things, and we want them to work in harmony. Next slide, please. So schematically, we have an engine underground with fresh air flowing over it. Now, nothing happens until we put a spark in that engine and we add diesel fuel, lubricants, and additives. And what comes out is heat, nitrous oxides, carbon oxides, DPM, and water vapor. Now, the worker that's on the right-hand side gets immersed into this cloud of dirty air, which is hot as well, and he starts breathing the particulates and the gases. Next click, please. So here what we can do is we can look at engine technology, as we said just now, fuel quality, and exhaust after treatment, which will take care of the particulates, the carbonates, and the nitrates. Okay. Click it again, please, Eugene. Okay, now what depends on it as well is the mining cycle. In other words, how you use this equipment. If you have LHDs in trucks, for example, you just have LHDs going up and down, and the ventilation strategy associated with that, because that dictates how much fresh air and air dilution, thank you, Eugene, one gets there. to be able to match the engine duty with the exhaust, the treated exhaust, and what we want the worker to be exposed to. Okay, so those are the three things that we need to combine. Again, I make the point, if this was a once-through system and the air on the right goes into the exhaust, it would not be a problem. And that is why also ventilation on demand with modulation can help in sorting out this issue. Next click, please. So, where do we start? Personal monitoring, let's start on the right. It's the one that we've been doing for a long time, and it was said it takes a long time to get an answer to the question. And anyway, we know that people that are going to be exposed are going to be affected. So it's a bit of a reactive, control or measurement, if you wish, and the measurement we use to control. Now, let's go to vehicle management and this issue. Okay, let me start at the top. Thanks. I think that's better to start at the top, which is the real-time environmental monitoring, diesel emission monitoring. And what I'm saying here, we can put sensors, and this is what I'm proposing, is that we sense the air coming into the section and the air going out of the section. We, as good ventilation officers, make sure that we've got ventilation zones that we can define and therefore measure. So we do this for fire detection, and we do this for environmental monitoring. But we can now also monitor the diesel emissions, which is the gases and the particulates, and transfer that information real time. And we can talk about the transfer of all of these data at the moment. Let's go down at the bottom. Vehicle management. I am proposing that on talking about emission-based management, we should only do that in a workshop. So we measure the unit, diesel unit that comes in the workshop. We do a tailpipe assessment. It goes through the paces and comes out of the workshop. The only time it will enter the mine is once we've done a tailpipe emission measurement and we log the information, and that meets a certain acceptance criterion, and we can come back to that in a minute. But all that information is then logged, so each vehicle has got a set of information that tells it when it was last maintained, what was the condition when it came in, and what is the condition when it was when it left the workshop. Then click again, please. And again, there we are. So we take all of that information. Now, it's three different sets of information. And then what we need to do is to filter that information. The one is real time, the one is personal monitoring, the other one is to the vehicle. But we can then combine it into and review the strategy to give us, for example, acceptance criteria for the vehicle, levels of vehicle exhaust when it leaves the workshop. How this can be helped is when we do the real-time management of the environment, we could be monitoring the units in that ventilation zone as well with the same technology. So it will tell us which LHD is in there, how long it's in that section, and if we're really going to get sophisticated, I'm not suggesting maybe that is the case, but we could also have a history of the cycles it went through. So we can combine that with the other data to come up with a strategy, a new cycle that will tell us what acceptance levels. We know what we want in the personal monitoring. We'll talk about it in a second. What the vehicle should do, and also if the ventilation rates provide the right level of dilution. Next, please. So very quickly. Managing carcinogenic substances, it's a stochastic effect. So what it means is that whereas we can talk about OELs, about other substances, it doesn't make sense when it comes through a stochastic effect like carcinogens. So to talk about the 160 microgram per cubic meter, to talk about 100 microgram per cubic meter, it's neither here nor there. Nobody will tell you that that is the case or that is acceptable. We're going to go as low as reasonably possible or achievable. But to do that, we need to have the full picture, and that's what instrumentation that we've just been talking about can give us, is where are we going in terms of environmental pollution, in terms of engine performance, in terms of worker exposure right at the end. Now, Andre, to answer your question, 0.06 cubic meters per second. The only time that in those tests we did with Sasol, we got anywhere near 0.06 was with the high technology filter, with the regenerative filter with 99% reduction in particulate. That's the only time we could talk about 0.06. I agree, it was a tier 1 engine, okay, but with filtration. So my suggestion is, if you have a tier 2, you should look at, and this is again gut feel more than anything else, but I would look at 0.1 to 0.15. Anything less than that, I'll be curious to see what the results would be in terms of what we can measure, which is probably exposure, worker exposure at this time. Next slide, please. So, if DPM reduction is our target, is that what we want to do? How are we going to work together to do that? And it comes back to Cas's point just now. Click, please. On one side, we have mining. They decide where they're going to mine, how they're going to mine, when they're going to mine. To do that, click. We've got engineering, which work together with the mining in terms of maintaining the equipment, selecting the equipment, repairing the equipment most of the time. Next, I like to put the ventilation, because it's a first, one of the first or alternative way of managing the emission if everything else fails. Next click, we have the supply chain. Supply chain speaks to engineering and mining. That's why we put it there. Click. And what's important is that mining selects the equipment. There is talk to the supply chain and back again, and things like filtration systems should be addressed there and then. Click, please. It's engineering in terms of service providers, what fuels are purchased, what additives are allowed in those fuels, what lubricants, maintenance regimes, and other equipment. Click. And the last bit, but definitely the not least, the occupational health and safety and health and environment aspects. Under occupational health, I would like to put the occupational hygiene and medical aspect of things more towards the worker exposure and looking after the worker. And only then we will really have, in my opinion, harmony in this symphony. Next slide, please. Thank you very much. Sorry I took long.
Marco, thank you very much for that detailed presentation and insights into all of the work that you've done by yourself and with all the other experts over the last couple of decades. There is a question from Martin. For the sake of time, Martin, I'm just going to keep this question for the end of our session. What we have as our last bit of content is from PINSA. So this is not a live presentation. We have Wayne Hose. He sent us his presentation pre-recorded. So it's a video that we're going to have a look at, just under 10 minutes. Before we watch the video, we can just give Wayne a couple of thumbs up and a clap and maybe a heart if we're feeling generous. So without further ado, let's finish up the technical content for the day. Once we're done here, we'll just hear some concluding remarks from Tim Nelson from AMS Hayden, and then open up the floor for general Q&A.
Hello and welcome to a very brief introduction to PINSA, the world's first and still the world's only fixed continuous real-time diesel emission monitoring system specifically designed for harsh environments.
Sorry for the pause. I just want to make sure whether everybody can hear the content from Wayne. Someone can just give me an indication in the chat box.
Can you put up the volume, Eugene?
All right, give me a second here. Let me resolve the issue. Apologies for this. It'll be sorted in just a second.
Hello and welcome to a very brief introduction to PINSAR, the world's first and still the world's only fixed continuous real-time diesel emission monitoring system specifically designed for harsh environments. At PINSAR, we believe that diesel fuel will be the predominant energy source underground, driving productivity for many years to come. And we also believe it can actually be managed safely. And with PINSAR being a practical technology, we're really supporting those decision-making processes as you manage your controls and work towards zero harm. The following slide will show a brief introductory video about PINSAR.
Until now, there was no commercially available monitoring system available for harsh environments. The PINSAR reader is a technological advancement and is revolutionary in the fight to detect and manage diesel emissions. It's fitted with a reader dashboard system and continuously monitors and records DPM levels within the critical 0 to 800 nanometer range, sends live data to control and response systems, as well as nominated users on multiple smart devices, potentially anywhere in the world, enabling real-time action and decision-making. It's able to detect and assess the presence of deadly DPM on a 24/7 basis, and DPM levels and trends, including shift averages, are continuously and immediately displayed along with key analytics. This allows global companies to monitor DPM data concurrently, continuously, in real time across multiple companies, divisions, and sites.
So what does PINSAR actually produce? Well, in consultation with some of the largest mining houses in the world, the discussion really revolved around the fact that it had to be an ultra-low maintenance product, which had to be robust for real-time continuous material monitoring because it was going to be in harsh environments. Now, this was the blueprint for the product, which was developed from the ground up. It's specifically designed for long-term deployment in very aggressive environments. It's now working in 6 continents, and very successfully with some of the largest customers in the world. So it's a very practical system, and really the practicality comes via the configurable dashboard, which is producing time-weighted averages, shift averages, 6, 8, 10, 12-hour shifts. You can look at data over a day, a week, a month, a year. And you're really looking at those trends over time. You want to know, is your DPM staying at the same level? Is it increasing, or is it in fact decreasing? And that's where the PINSAR system plays the biggest role. So the existing technology is well known to the industry. Tailpipe testing above ground, gravimetric testing, and handheld monitors underground, which are in fact real time. They're just not continuous real time, and they require manual intervention as well as filters and change of batteries, etc. But they're all random intermittent spot checks, point in time validation. They're all part of the picture, but they don't form the whole picture. And what we believe is to manage your controls effectively, you really need to adjunct these products or augment them with 24/7 monitoring. And that's where PINSAR fits in. That fixed time, real-time continuous monitoring allows you to validate controls and move very quickly on exceedances with control and responses. So it's a bit like finding a needle in a haystack without a fixed real-time monitor, because getting results back from a gravimetric reading some 2 to 6 weeks later, it makes it very difficult to circle back on what was the emitting technology, where was the exceedance, and how to control that for the future. Almost impossible, in fact. But ultimately, what we'd all say is these systems work together in an ecosystem under the management of a diesel particulate management committee, which tends to be the missing link at most operations. And that coordination between hygiene, ventilation, fleet, and senior management, we believe, is critical in the process. So what we're discovering about the Pinsar reader is that different customers are deriving different benefits from the product. It's true to say that some customers just use the DPR to gain access to data, and that data can be sliced and diced very quickly and sent upline to management. And that's a really key benefit of the product, we're told. Other customers are using it more around having access on their mobile phones and desktop laptops through SCADA systems, whereby it's really working on those control and responses within the business. Other customers, I guess, are using it more around reducing their OELs and supporting ALAR within the business, or towards a genuine desire to work towards zero crime. And finally, the second to last presentation slide, the final slide will actually be a inserted video, which will actually show a ventilation simulation, which is enabled in this case by Pinsar, and we're uniquely positioned to do that. Now, in this case, it's a VentSim control and response system. Pinsar can, of course, enable other systems like Vuma 3D, etc. And I guess the last trend I'd like to talk about today is VOD. I guess VOD, ventilation on demand, whether it be full ventilation on demand or limited ventilation on demand, is becoming a bigger global trend. And it gives the customer ultimately the ability to reduce electricity usage and therefore derive a significant cost benefit from that technology. So in conclusion, we thank you for your time today. We hope you enjoy the rest of the webinar. Take care.
Hi everybody, my name is Anthony Bamford. I'm a certified occupational hygienist with past ventilation officer experience, working for GCG Green Consultant Group. Today I want to demonstrate how real-time monitoring, in this case fixed real-time monitoring data, in this case it's VentSim. VentSim is used in mining as a tool to do long-term mine planning, ventilation planning, as well as day-to-day planning for the ventilation network. What you can see at the moment is a longwall coal mine. The two call-out boxes here are where the Pinsar units are installed. I'll start this model off. So what you're seeing right now is on the right hand side here is the time. So every increment's kind of like a minute, and like I said, it's 1 day's worth of data. So I'll start this model off. And as you can see, the DPM is already spreading through the mine, and it's 20 minutes in to the model. Zooming into a specific area, you can see there's a constant reading of a DPM of 0.04 more or less, and you'll see like there a big spike come through. Could be that a machine is just has been working upstream of that sensor and just pulling a load, and that DPM plume that it created past that point, and then that will go through the mine right out up to the fans, which is located here. So you can see as it gets closer to the fan, it starts diluting a lot because it mixes in with air that might not have DPM, and also mixes in with higher ventilation flows. Another nice function VentSim has is actually these data boxes. So this specific data box displays the DPM reading in this airway as a live function. So whatever it sees there, it'll display in that data box. Obviously, nice to have it to display this up in a control room or one that's shown in a presentation somewhere. To change your perspective on how we look at occupational hygiene risk is we're looking at this in real time or very soon after the exposure occurs. So you can take action. Where compliance monitoring is very reactive, there's not a lot a mine can do 2 weeks after an incident's occurred, or it's often very difficult to find out what went wrong. So very handy to try and incorporate this on your sites, and this can be used all over, coal mining, metal mining, tunneling. which I think is a really interesting one to have this in at the moment. As well as if you had buildings, workshops that's got fixed airflow.
Thank you very much, and thanks to Wayne Hose and the team that put together that content to end off our workshop. Apologies for being 1 or 2 minutes behind schedule, but we are done for the day in terms of the technical content. And at this point in time, Tim, I invite you, the floor is yours to just give a couple of concluding remarks. And thanks to everybody that participated, everybody that took time out to listen to all of us today. Tim, the floor is yours.
Hi colleagues, good day to all. I'm Tim Nelson from AMS Hayden, and I just want to take this opportunity to thank all the sponsors, the speakers and the participants for their time and input in sharing information and experience on this serious topic of DPM. AMS Hayden, together with our product OEM Pinzar, have made contact with many people in this industry on this topic, and we have realized the need for information sharing. Together with the speakers and the consultants, we want to make ourselves available to give you further information and support with your DPM risks and management programs. And please feel free to contact us, and also please follow us for more exciting webinars and relevant topics and applications and technologies to follow. And thank you all so much, and be safe.